Hello, welcome to the Area Solutions channel. In this video, I'll be looking at an example that borders on systems of particles, which is a branch of kinetics that discusses the motion of several particles, wherein the movement of one particle affects the movement of the others. And we're going to walk through this example. We have that for the figure shown. Block B moves down with a constant velocity of 50 millimeters per second. We have that the acceleration due to gravity of block B at every point in time is 0. Then at time t equal to 0, block A is moving upwards with a constant acceleration, and its velocity is 70 millimeters per second. As we begin to solve this problem, we're going to see why we're taking the velocity as negative 70 millimeters per second. But to proceed with the parameters that are given unto us, we have that at time t equal to 4 seconds, the slider block C has moved 70 millimeters to the right. And we're asked to determine the velocity of the slider block C when time is 0, the acceleration of A and C, that's block A and C, as well as the velocity and displacement of blocks A, B, and C after 12 seconds. To solve this problem, we want to start by first looking at the coordinates. For this particular problem, we're going to take the coordinates such that if you're moving away from the system, from a particular point of the system, we take it as positive. Then if you're moving downwards, it's positive. That is to say, when block C moves away from the system, we have it to be positive, and when block A or block B moves downwards, we have it to be positive. Contrarily, if they move in the opposite direction, say block A or B moves upwards, we take the velocity or displacement or acceleration as negative. Likewise, if block C moves leftwards, we take it as negative. So we have our coordinate system. Positive is towards the left side of the system, and downwards of the system we give us our positive directions respectively for the horizontal and vertical axis. So going back to the problem that we have, we want to quickly derive what you call a unique equation that relates the motion of the different parts, what we call relative motion of one particle with respect to the other. We have that this particular string is connecting the different bodies together, A, B, and C, such that if we say the part shown is S1, the second part is S2, we have other parts S3, S4, S5, S6, X7, and X8 as well. These different parts combines together to give the length of the string. Let's say that's L, such that we have X1 plus X2 plus X3 down to plus S8 is equal to L. If we consider that block C moves to the right, and that will cause block B to be displaced upwards, and that will make block A to be displaced downwards, such that we can have the system at a particular time to be as shown. If we look at the different dimensions of the string x1, x2, x3, we can quickly say that x1 is equal to x2 is equal to x3, and we can call that xa. And also, because the different parts of the string that are attaching block B to the pulleys are equal, as can be seen, we can say that x4 is equal to x5 is equal to x is equal to x7, and we can call that xb. And likewise, we can call the part attaching block C to the system, which is shown as S8, to be equal to SC. So having considered that, we can replace the dimension of the system to be XA for the parts that are attaching block A, SB for the part that are attaching block B to the system, and SC for the part that is attaching block C to the system, such that if we recall our equation x1 plus x2 plus x3 plus up to x8 is equal to L, we can quickly replace that by their respective symbols XA, XB, and XC. So once this is done, we can have a better simplified equation as 3xa plus 4sb plus xc is equal to L. That's the length of the string. So if we have this particular equation, we can quickly find the time derivative of each and all of the components of this equation. So if we differentiate this equation with respect to time, we have something like this: 3x dot a plus 4x dot b plus x dot c equal to 0, where s dot represents the time derivative of x. So we can say that when you differentiate sa with respect to time, you have s dot a, which is the same thing as dsa dt. Likewise, s dot b is the derivative of xb, and x dot c is the derivative of xc, and these are the velocity components. If you differentiate L, you get 0, knowing that the length of the string is constant for every point in time. And if we differentiate these velocity components again, we get another equation such that we have 3s dot dot a plus 4s dot dot b plus s dot dot c is equal to 0. And we know that s dot dot a is the time derivative of s dot a. Likewise, we have the same for s dot b and s dot c, as well as when we differentiate 0, we get 0. And these are the acceleration components for this system. And these three equations are vital for analyzing the motion of any block or any parts of this system. So going back to the question, we have our variables given unto us. We have the initial velocity of block B and the acceleration of block B. We also had some variables given to us for velocity of for block A. We had the initial velocity of block A to be minus 70, and it is minus 70 because we said any part that is moving towards the system is negative, such that as A is moving upwards is negative, and any part that is moving away from the system is positive. That's why for velocity of B, we had it as positive. And finally, we're given some variables for C as well. We're given the displacement of C after 4 seconds. And it's positive because it's moving away from the system. It's moving towards the positive direction of the x-axis. And we're told to find the velocity of slider C when time is equal to 0. To solve this problem, we're quickly going to call our equations of motion as well as the equation that relates to different parts of the system. So we have our basic equations of motion for rectilinear motion, and we have our 3 equations that we derived that relate the different parts of the system as they are moving relative to each other. So for this, we're going to look through these equations and try to identify which one is most suitable for calculating the velocity of particle C, more particularly the initial velocity of block C. If we look at the first equation, we have that V1 is equal to V0 plus AT, that is final velocity is equal to initial velocity plus acceleration times time. And if we look at what we have for block C, we are looking for the initial velocity, which is V0 in this case. We don't have the final velocity, we don't have the acceleration, so we cannot use this equation. If we go to the second equation, x1, which is displacement, is equal to the initial displacement, which we always assume to be 0, plus initial velocity times time plus half acceleration times time square. If we look at what we have again for particle C, we don't have most of all these terms. We don't have the acceleration. Of course, we have time and the final displacement, but we're looking for initial velocity. So we cannot use this equation because we have 2 unknowns, which are the acceleration and the velocity. If we look at the third equation as well, it's also invalid because we don't have the final velocity V1 and we don't have acceleration, and we're looking for initial velocity. So because because this equation has more than one unknown, the initial velocity which we're looking for, we cannot use it. And these other sets of equations that we want to begin to look at looks at the entire system. What are the variables we have for other parts? Can we use the variables we have for other parts to identify or to look for the one we don't have? For this case, if we look at the first equation among the relative motion equations, we discover that this equation relates displacement, but what we are looking for is initial velocity, so it's not valid. If we look at the second equation, Amongst the relative motion equations, we discover that this one relates velocity. So we have 3 times the velocity of particle A plus 4 times the velocity of particle B plus the velocity of particle C is equal to 0. Of course, we have the initial velocity of particle B, we have the initial velocity of particle A. So this equation can be valid to find the last term, which is the velocity of particle C. And finally, the last equation, we cannot use it because it relates acceleration components. So working through to get our solution for this problem, we're going to call our equation that we've identified that could be useful for solving this problem, which is the equation that relates the velocity of the different particles in the system. So if we write it properly based on the variables we've been using, we discover that for the new equation, S dot A is being replaced with the initial velocity of particle A. S dot B is being replaced with the initial velocity of particle B, and S dot C is being replaced with the initial velocity of particle C. That's V naught C. And of course, 0 remains 0. So because we have all these variables, if we put them into the equations, for initial velocity of particle C, we had it to be minus 70 millimeter per second. For the initial velocity of particle B, we had it to be 50 millimeter per second. And of course, we are looking for the initial velocity of particle C. So by the time we relate them and simplify this equation, we get our initial velocity of particle C, that's the velocity of slider block C at time equal to 0 to be equal to 10 millimeter per second. So that's that about the first question we are to answer for the particular sample problem we're working with. The second question asks us to look for the accelerations of block A and C, that's AA and AC. Mind you, we've estimated the velocity of particle C earlier to be 10 millimeter per second. So we're going to call all our equations again. We have 6 primary equations. The first 3 are motion geometry equations. That's equations of motions that are used to estimate the motion of a particle at every point in time. And the second set, that's the last 3 equations, are the ones that relate the movement of one particle of one of the slider blocks with the others. So we're going to look through these equations one by one and see which one is suitable for estimating either acceleration of block A or acceleration of block C. If we look at this first equation, we can first and foremost look at block C. What do we have for block C? Because we are looking for acceleration of block C as well. We have the time, we have the displacement, and we have the velocity. What we're looking for is acceleration, we have time, we don't have final velocity, so this equation may not be useful. Then if you look at the second particle as well, block A, you discover that we have just initial velocity, we don't have final velocity, we have time as well to be 4 seconds. But because we don't have 2 unknowns, that's the final velocity and the acceleration, so the equation can also not be suitable for looking for acceleration of particle A. If we go to the second equation, we see that the second equation relates displacement, final displacement, the initial velocity, the time, and the acceleration. Now, if we look at particle C, can this equation be useful? Yes, it can, because we have the final displacement to be 75 millimeters. Initial displacement, we know it's always 0 because the object will start from the origin. Then we have our initial velocity. We've estimated it earlier to be 10 millimeter per second, and the time is 4 seconds. But we're looking for acceleration, so this equation can suitably be used to calculate the acceleration of particle C, that's block C, at every point in time. Then what about the other block? We cannot use it to estimate the acceleration of block C because we have just the initial velocity of block C. So this equation may not be valid to estimate the acceleration of block C. Then we move on to the third equation. This equation may not be valid because, as we can see in this equation, we have a number of unknowns. We don't have final velocity for any of the cases, and we don't have acceleration that we are looking for. So both for block A and block C, this equation is not valid. If we look at the next equation, we see that this equation relates displacements. But we're not looking for displacement, we are looking for acceleration, so it's not valid. If you look at the next equation, the next equation relates velocity. It's also not valid because we are looking for acceleration components and not velocity. So by the time we go to the last equation, we see that this equation relates the acceleration of the different components. Of course, we have the acceleration of B already given to us as 0. Of course, we also have the acceleration of particle C. By the time we use the equation that we identified earlier to determine its acceleration, and so we can use this particular equation eventually to estimate the acceleration of block A. And that will be all. So we're going to walk through these two key equations that we've identified. First, we'll look for the acceleration of particle C, that's block C. Then we'll use the second equation we've identified to find the acceleration of block A. So to start with what we have, we said this particular equation can be used to work on particle C to find the acceleration of particle C. So if we replace that by the variables we have the displacement when the time is 4 seconds, that's xc4. We have the initial displacement, which we said is always 0. Then we have the velocity, which that's the initial velocity, which we estimated to be 10 millimeter per second. And of course, we are looking for acceleration, and we have our time to be 4 seconds. So we can input all these values into the equation that we have, and we're going to get 75 to be equal to 0 plus 10, which is the initial velocity, times time is 4, plus half times the acceleration we are looking for, times the time, which is 4 raised to the power 2. And if we evaluate this, we get that the acceleration of particle C, that's block C, is equal to 4.38 millimeter per second square. So we can bring that into the list of parameters that we have. We have that acceleration of block C is now 4.38 millimeter per second, and we have the second equation that I want to use to estimate the unknowns for block A, that's the unknown acceleration for block A. And of course, we have different items that have been identified, but first we need to replace this particular equation with the variables that we've been using, the designation of variables that we'll be using. So s dot A is same thing as AA, s dot B is same thing as A subscript B, and s dot C is same thing as A subscript C. So if we input all that we have into the equation, we're looking for SA, so it's an unknown. We have the acceleration of B to be 0 as we're given in the question, and we have estimated the acceleration of AC to be 4.38. And if we simplify this equation, we get the acceleration of block A to be equal to 4.38 over 3, which is equal to 1.46, and it's negative because of course we said A was moving upwards. We have calculated the acceleration of block A and that of block C. So we move onward to the next question that requires us to determine the velocities and displacements of blocks A, B, and block C. Now, to determine this velocity, we first need to determine these values. We first need to input all the variables that we've estimated. For block C, we've estimated the velocity to be 10 millimeter per second and the acceleration to be 4.38 millimeter per second. And we have also estimated the acceleration of block A to be minus 1.46 millimeter per second. So we bring forth our equations. We have 6 basic equations that are useful for this particular problem. And we assess the first one. Can we use this first one to find velocity? Because this equation relates initial velocity, acceleration, and time. We have the time to be 12 seconds as given in this problem. We have our initial velocity to be 10 millimeter per second for block C, and that of block A to be minus 70 millimeter per second. And of course, we have the initial velocity of block B. And we have acceleration for all these blocks. So we can use this particular equation to estimate the velocities for the different particles that is being considered, A, B, and C. Then if we look at the second equation, can we use this equation to find let's say displacement, because of course we've identified the equation that we can use to find the velocities. The next we want to know which equations can we use to find displacements. If we look at this second equation, x1 is equal to x0 plus v0 t plus half at square, we discover that for what we have for the different particles that we have their initial velocities, we have the time. They said the time, we have to estimate these values for when time is 12 seconds. We have accelerations for every one of them, and we have their time, and we have time again as well. Now, because we have initial velocity, the acceleration, and time, this particular equation can be useful to find the displacement of all of the particles. And of course, if we walk through all that, we discover that others, well, they may be useful by the time we begin to calculate, but they may not be straightforward. So we're going to stick to the first two equations. What I mean by it may not be straightforward is that if you use any of these equations, you may need to estimate a particular unknown variable first before you can suitably apply the equation in question. So we're going to stick to the first two that we've identified to estimate the velocities and the displacement for the systems respectively. So to proceed from there, we're going to start by first estimating the velocities for the different particles. V1 is equal to V0 plus AT, and we're going to start with particle A, that's block A. So if we input all we have for the particular variables for block A, VA12, because we are looking for the velocity when the time is 12 seconds, it becomes V1 is equal to VA0, that's the initial velocity of block A, plus the acceleration of block A, that's A subscript A multiplied by time, wherein time is 12 seconds. And of course, we have all these already gotten from previous calculations. So by the time we input them into the equation, we have that the velocity of particle A can easily be estimated to be 87.52 millimeter per second. If we do same for particle B, if we input all the variables that we have for particle B, let's not forget that the acceleration for particle B is 0 because particle B was moving with constant acceleration. So if we estimate that, we'll get the velocity of particle B when the time is 12 seconds will still be 50 millimeter per second. And finally, for particle C, we have that VC12 is equal to VC plus A subscript C times time. If we input all the variables we have for particle C, we can estimate the velocity of particle C when the time is 12 seconds to be 62.56 millimeter per second. So having done this, the next is to estimate the displacement for each and all of the particles. Because it's straightforward, we already have our equations and we have all the variables already known from previous calculations. We just input them into the equations and we estimate our value. For the displacement of particle A, we have it to be minus 945.12 millimeters. For that of particle B, if we do same, we have the displacement of particle B after 12 seconds to be 600 millimeters. And finally, for particle C, if we do same, input all the known values to estimate the displacement when the time is 12 seconds, we have that the displacement of particle C is 435.36 millimeters. So after this is done, I think we're done with everything that is required of us. Let's not forget, we're giving certain variables for particle B, that's block B. We're giving also for block A, and we're giving some for block C. And we use our basic equations first and foremost to estimate the velocity of particle C. Then we found the acceleration of block C and that of block A. Then after that, we estimated the velocities for the different blocks, that's for block A, block B, and block C. And finally, we estimated the displacement for block A, block B, and block C. So I think these are all for this particular problem. There's something very striking that we must always note. For every system, we must be able to first derive the equation that relates the motion of one particle to the other. Once that is done, you combine those equations that relate the particle's movements to the basic equations of motion to determine every form of unknown that is in the problem. So we're going to look at another tweak to this question. And we're told that for the system shown, block B starts from rest. When you hear the word block B starts from rest, that indicates that the initial velocity is 0. And block A moves with a constant acceleration. Of course, block B starts from rest, block A moves with constant acceleration. And we're told that slider C, that's block C, moves to the right with a constant acceleration of 60 millimeter per second square. Then we're told that when time is 5 seconds, the velocity of B and that of C are 450 millimeter per second and 240 millimeters per second respectively. So we have all these variables given to us. Then we are told to determine the accelerations of A and B, the initial velocities of A and B, the change in position of slider blocks A, B, and C after 6 seconds. So to solve this problem, we need to call our equations. Let's not forget that because this particular problem is similar to the one that we just solved, we just tweaked the variables that are given from one known to an unknown. We must note that these same relational equations are also valid, but it being the pulleys of another configuration, we may first need to derive the relational equations to solve these problems before we start combining them with the basic motion equations for particles kinematics. So the first part of the question asks us to determine the accelerations of A and B. And of course, if we bring in all our equations one per time, we see that for this first equation, velocity v1 is equal to v0 plus at. Can we use it to find the acceleration of particle B? Well, look at the system of B. We have initial velocity to be 0, we have final velocity to be 450, and we have the time of that final velocity to be 5 seconds. So this first equation can be valid to determine the acceleration of particle B. But can it be used to find the acceleration of particle A? No, because we don't have much variable given for particle A apart from its velocity. So if we look at the second equation, can it be useful for particle A? No. Can the third be useful for particle A? No. Then we look at the next equation. This is one of the relational equations, but this one talks about displacement. That is, it relates the displacement of the different parts of the system. So it's also not valid because it does not have velocity component of particle A, which we are still struggling with. Then the third equation relates the velocity of the different components, but relates the velocity of the different components, so we cannot use it to estimate acceleration of particle A. And finally, the last equation relates the acceleration of the different blocks that is attached to the system. And remember that we can use the first equation to calculate the acceleration of block B, and we have been given the acceleration of block C. So this third equation can thus be used to find the acceleration of block A, noting that we have acceleration of block B and we've estimated for acceleration of noting that we have acceleration of block C and we've estimated the acceleration of block B using the first equation. So we're going to proceed by solving this problem. We have two equations that are valid. So we're going to use the first one, v subscript 1 is equal to v subscript 0 plus at, to estimate the acceleration of block B because we have its initial velocity and the final velocity when the time is 5 seconds. So if we bring in the core variables that describes particle B, v subscript b5 is equal to b subscript b0 plus a subscript b times time. If we input all that we have the respective values into the equation and we simplify, we can quickly observe that the acceleration of particle B is 90 millimeters per second. Then if we were to work with the second equation to estimate the acceleration of particle A, the first thing to do is to write it in the proper designations. Let's not forget that we've estimated the acceleration of particle B to be 90 millimeters per second, and we have the acceleration of particle C to be 60 millimeters per second. So if we put all these into the equation that we are working with, we have 3 times acceleration of particle A plus 4 times 90 plus 60, which is the acceleration of particle C, all is equal to 0. And we can simplify this to get the value of acceleration of particle A to be minus 140 millimeters per second. The negative sign there informs us that block A is accelerated and is moving upwards. That's moving towards the system. So the next part of the questions asks us to find the initial velocities of A and C. That's VA0 and VC0. We're going to walk through this problem, but first, to walk through this problem, we may need to first bring in some of the things we've estimated. We've estimated the acceleration of block A to be minus 140 millimeter per second square, and that of block B to be 90 millimeter per second square. So having all these parameters as it is, we may need to look through our equations to see which is valid. The first equation on our list is V1 is equal to V0 plus 80, and we're looking for initial velocities. If we look at initial velocities for block A and block C, if we look at block C closely, you will see that we have the final velocity when the time is 5 seconds. We have the acceleration to be 60 millimeter per second square, and we have the time, which is 5 seconds, and we're looking for initial velocity. So this equation is valid. So we go onwards to estimate the value of the initial velocity using this equation, and once we simplify, we can get that our initial velocity VC0 is equal to minus 60 millimeter per second. So initially block C was moving towards the left, but as it is now, block C is already moving towards the right. That's why at 5 seconds we add it to be 240 millimeter per second. And then next we want to look for the velocity of particle A. Which equation is suitable? We know that because for particle A we have just the acceleration, we don't have initial velocity, we don't have final velocity. So the only equation that is valid is the equation that relates the velocity of the different particles. And if we are to estimate that using what we have, we know that we have the different velocities. We have velocity of particle B, we said it started from rest to be 0. We put it into the equation, and we calculated the velocity of C earlier to be minus 60 millimeter per second. So by the time we simplify this, so we have the initial velocity of A to be 20 millimeter per second. The next part of the question requires us to find the position of the slider ABC after 6 seconds. That's XAC, XBC, and XCC. To do this, we of course need to bring in all the variables that we have, and we pick the equation that is valid. This equation x1 equal to x0 plus v0 t plus half at square is the most suitable for estimating displacement. So if we input the correct variables based on what we have and we estimate displacement for each and every one of the block, we discover that the displacement of particle A after 6 seconds will be minus 240 millimeters. That of particle B will be 1620 millimeters, and that of particle C after 6 seconds will be 720 millimeters. So invariably we can note that these are the values that has been calculated based on the equations that we have, and we may want to try our hands on this problem, which is similar to the first problem that we solved, and the answers, they are likely going to be based on the previous example. All the variables remain the same in terms of their values. So walk through this problem to see if you fully grasp the concept that has been explained in this video. And this will be all for now. I want to thank you for watching, and please do well to subscribe to my channel.